is StarTalk. Neil deGrasse Tyson here, your personal astrophysicist. I got with me Chuck Nice. Chuck, baby.
Hey, Neil, what's happening?
All right, we're doing cosmic queries today.
Yes.
Yeah, and you collect them, and we bring in an expert.
Yes.
To help it out.
Yes.
And today we've got a friend and colleague, and a friend of StarTalk and a friend of mine, Matt Dowd. Matt, welcome back to StarTalk.
Great to be here again, Neil.
Yeah, your expertise is black holes, quasars, gravitational lensing, really juicy, tasty, cosmic things, all of which will kill you if you come in the vicinity of them.
Immediately.
The most hostile part of the cosmos.
Exactly.
That's why we love them.
You teach at Lehman College of the City University of New York.
That's right.
You're also an associate here at the Department of Astrophysics at
Indeed.
the American Museum of Natural History. And you're a host and writer for the YouTube channel for PBS Space Time.
Yeah.
Which has nearly 3 million subscribers. Dude, you're rocking it. Totally killing it. So what is this film you were part of? You got some other thing you were, Inventing Reality. What is that?
Yes, Inventing Reality.
It's called U.S. Politics.
It's exactly right. Yeah. This is a film that we recently got crowdfunded, and we're in the process of writing.
Love that. Okay. And what's it about?
It is about our quest for the fundamental. It's about humanity's search for the underlying clockwork of nature, both from the point of view of physics, but also from the point of view of neuroscience, brain science. So it's connecting how our brains construct our models of the world and how that fact is connected to how science at a societal level constructs its models of the world.
And you have a collaborator?
I do. So working with my partner, Bahar Golipur, who's a neuroscientist, we're writing it together, and it's being produced with and directed by Andrew Kornhaber, who's part of the Space Time team.
Okay.
Very nice. Very nice.
So everyone should have like a neuroscientist at arm's reach. I always think.
100%.
Without a doubt.
I'm not alone. I'm not alone in that.
Except I have to pay mine by the 45 minute. But I do have one at arm's reach.
Yeah. So, Chuck, we've got questions.
We do.
They're solicited from our Patreon members.
Correct.
The threshold of access to this feature is $5 a month.
That's it.
So that's all it is.
That's it. Cup of coffee.
All right. So, Matt, are you ready for us?
Let's do it.
Let's do it. All right. All right. By the way, Matt and I have overlapping expertise in the Venn diagram. So what'll happen is that whatever is right in his bailiwick, he'll take it. But if there's some spillage, I'll jump in too. You okay with that, Matt?
Let's do it together.
Okay. All right.
There you go. Look how Matt.
And if the spill is from that, then Chuck can pick up the slack.
Right. At that point, we're not looking at spillage. We're looking more like at an environmental disaster.
Okay.
You know what I mean? That's kind of Exavon Valdez territory. It's like, and Chuck, what do you think about black holes? We have reached a new low. Okay, here we go. This is BSM 1989. Says, greetings, Dr. Tyson, Chuck, and Dr. Matt. Well, my name is Blake, and I'm from Mobile, Alabama. Can you elaborate on energy density surrounding a black hole and how Hawking radiation might work? Is the material that falls into a black hole lost forever? And does it eventually somehow get out?
Love it. That's all you, Matt. Take it.
Wow. All right. So to answer this question, I need to summarize a large fraction of 20th century physics. Wait,
but we only have like...
I know. I'm going to try.
You're going to start your answer by saying, first let me summarize 20th century physics.
No,
here
I'm
we go,
serious,
guys.
because...
The answer to your question is, I was born the son of a poor sharecropper.
Yeah, exactly.
That's how it
I mean,
begins.
there's so much of the story of the development of 20th century physics is around black holes, and this exact weird thing about black holes that what goes in seems to not come out, and this is a paradox. Okay, so all right. So first of all, let's talk about a black hole. It is a place where gravity has had its ultimate victory. So it's usually the collapsed core of a star. So you have this hyperdense region where it is the gravity is so strong that light can't escape. Okay, we don't know what's really inside a black hole, but there's this region around whatever that collapsed object is, where you have what we call the event horizon, and that's the distance from which light can't escape, and it's black. Okay, and so these things are invisible, unless they're eating a star or a galaxy or something, and then we see the mess they make. But back in the 1960s, Stephen Hawking realized that black holes shouldn't actually be completely black; they should radiate. And this was Hawking's most famous discovery, called Hawking radiation, and it's described in a couple of different ways. One way is that you have matter and antimatter particles spontaneously appearing near the event horizon. Normally they would vanish again, destroying each other, but if one gets sucked into the event horizon, the other can escape. Okay, that's sort of the pop sci level. Hawking's own description of it was talking about the positive and negative frequency modes of the quantum vacuum and how they get perturbed by the black hole, leaving the vacuum itself generates particles which you see. Okay, so Hawking radiation causes black holes to leak away their mass. So there's the answer to the other part of the question. When something falls into a black hole, we think now. So originally we thought that nothing could escape a black hole because nothing can travel faster than light, right? But now I think most physicists believe that because you have this Hawking radiation, at least the energy that falls into a black hole can eventually leak away as that radiation. And the really important thing about that is that not only can the energy get out, but the information can get out. And this was the other perplexing thing about black holes. It shouldn't be possible to destroy what we call quantum information, but via Hawking radiation, many physicists now think that the details of what you threw into the black hole somehow get out via this Hawking radiation also.
So they get remembered. They get remembered.
Right, yeah.
Exactly.
So it's almost like whatever it is, although it's not a chair that went in, all of the things, the blueprint information on that tiny level, when it comes out, that is still available.
Yeah, if you could go to if you could collect all the Hawking radiation that evaporated out of a black hole over trillions of years, like every little bit, and somehow piece it together, the worst jigsaw puzzle in the universe,
right?
You should be able to reconstruct the chair.
Right. And that's what you guys mean when you say information. You're talking about all the stuff that we actually are on the
inventory, the particle
inventory on the quantum, right, all the way down to the particles.
Yeah, the information that you would need if you wanted to rewind the universe and find out what happened previously. If you had all the information, then in principle you could run the clock backwards and figure out what fell into the black hole in the first place.
And just to clarify a point you're making, you're saying it came out of the black hole, but in fact it came out of the energy field in the vicinity of the black hole, which counts as coming out of the black hole. Is that right?
Thank you for getting to the biggest hole in my argument here. Hawking's arguments were based on sort of internal consistency arguments in that it had to exist for the universe to make sense, but the actual mechanism of its creation isn't clear. We just know it has to sort of emerge from the vicinity of the black hole somehow.
But that counts for having come out of the black hole because it's using the gravitational energy density created by the black hole, and it just happens to be outside of the event horizon, right?
Yeah. So one description of how this happens is that the thing that falls into the black hole, which is your antiparticle or your negative frequency mode or whatever, somehow gains negative mass or negative energy inside the black hole, because the dimensions inside the black hole get all twisted around, and so it's possible to have this relative negative mass go inside, which causes the positive mass of the black hole to shrink a little bit.
Wow. Okay.
No, Chuck, isn't that obvious? That's completely obvious.
My God, that is insane. I love it. Wow.
All
okay.
right. All right,
wow.
keep going.
So cool. Here we go.
Chuck.
Hello, Dr. Tyson, Dr. O'Dowd. How do we know black holes follow the second law of thermodynamics? Can black holes be regions of fixed entropy.
Ooh, I like that. Because, Matt, we say the second law of thermodynamics, in a way that's an observed phenomenon, right? There's no deep principle deeper than it. We just say, looks like entropy increases everywhere, so let's make it a law, and maybe the black hole violates this.
This is such a good follow-on question. The crazy thing about entropy is that it feels like it's something that just emerges from the way particles interact with each other, etc. But it also seems like one of the most fundamental things in physics, because no matter where you look, entropy seems to increase. With a black hole, there is a way to think about its entropy. So we think of entropy as a measurement of the amount of disorder in a system. Okay, so a system will always move towards states of more disorder. Okay, think about, for example, the air in the room. If you took all of the air and compacted it down into, a ball this size, it would, well, first of all, you'd die of asphyxiation immediately, but the air would immediately burst out to fill the room. Okay, this configuration where all the air particles are in this one spot, it would be considered a very special or very ordered configuration, and so it would be considered low entropy. So the only thing it can do from there is expand into a more disordered arrangement, fill the room. That would be high entropy. In the case of a black hole, we can think of their entropy as in terms of information, okay, just like we talked about. So in the case of the air in the room, when the air fills the room, we know a lot less about the location of the particles of the air molecules. Okay, so we have very little information. There's a lot more hidden information in the air in the room when it's filling the whole room, compared to if we have this ball of air in our hands, then we have a much better idea of at least the location of all of the particles. They're all in this ball of air. Okay, so entropy can be considered as a measurement of the amount of hidden information in a system, and over time, we tend to lose more and more of the information of a system. So for a black hole, as a black hole grows, it's swallowing things from the external universe. And because we can't get information about what fell into a black hole out very easily, as a black hole grows, its entropy increases. Okay, so the amount of hidden information increases. And so there's this very tight relationship between actually the surface area of a black hole and the amount of stuff that it's eaten, which corresponds to the amount of information that that black hole is hiding. And so I won't get into the next point, but I got to mention, it was this simple observation that the entropy of a black hole is proportional to its surface area that led us directly to the holographic principle, the notion that the information of the interior of a volume can be completely encoded on the surface of that volume. And it led people like Leonard Susskind and others to realize that you could actually encode the interior of a universe on its surface area. And that's another story that led directly from this notion of black hole entropy.
Interesting.
Okay, so we're all two-dimensional holograms. That's the takeaway on this.
That's the takeaway.
That's it. There's your real answer.
Chuck, I always knew you were just a two-dimensional person.
No, what you meant was that I thought you meant my character was
okay,
not my physicality.
All right. All right, give me another one, Chuck.
That was cool. So, by the way, I don't know if I said that was Deepan Das. That was the person who gave us that. Deepan Das.
Oh, Deepan Das. Okay.
Deepan Das. Okay. And this is Anthropocosmic Dylan. Anthropocosmic.
I like it. Mm-hmm.
Yeah, very cool. Hello, Dr. Tyson, Dr. Dow, Dr. Comedy. In space documentaries like PBS Space Time, they talk about future cosmic events in distant galaxies on Earth timelines. Instead of saying the sun will blow up in 5 billion years from the perspective of a galaxy far away, how do you adjust for the time dilation so that the information you're talking about is correct in the instant. In terms of relativity, it seems like galactic simulations sort of step through a wormhole to film solar systems. Or that should be exosolar, because
So in other words, what is the rate at which time ticks on things we're observing? And if it's not ticking at the same rate that it was ticking here on Earth, who are we to put it on our timeline?
On the Earth timeline.
That. Why don't we pick that up when we return in segment 2 on StarTalk Cosmic Queries? Weird, wacky stuff that our guest, Matt O'Dowd, is an expert in when StarTalk returns. We're back. StarTalk Cosmic Queries.
Yes.
Got Chuck with me. Chuck, you still there?
Yeah. I'm still
hanging with us,
man.
There's some deep stuff coming down here. Matt O'Dowd, friend and colleague from Lehman College of the City University of New York. So you are expert in this session. We've got you in for like quasars and black holes and weird, wacky, fun things that will kill you post haste in the universe. So what else you got?
So what we were talking about before the break was from Anthropocosmic Dylan, who is actually Dylan from San Diego. In the short, what he was talking about, it seems like galactic simulations kind of step through a wormhole to film exosolar systems, because, you know, they're not really on our timeline, but we put them on our timeline. So what's the deal?
What's up with that? I mean, yeah, how do we reckon the relativistic effects, time dilation in an expanding universe on a timeline that we're just trying to set up for the universe here on Earth?
Shall I take a shot at this, Neil? Or
yeah, please. Yeah.
Let me do it.
I just asked you. I asked you because I don't want to answer.
All right.
I'm leaving this for you.
So the stuff that I study is far enough away that this matters. Many of you have heard that the universe is expanding, which means that distant galaxies appear to be moving away from us. And you look far enough away, they're moving away from us at a big fraction of the speed of light. Okay, and so Einstein showed us that the rate at which your clock ticks depends on your motion, and the rates that you see a clock ticking depends on the motion of that clock relative to you. Okay, so fast-moving objects, you see that their clock appears to be ticking slower, right? And so I, for example, study quasars in the very distant universe, and we really have to take this into account. Okay, so we might see these quasars fluctuating. Okay, these are supermassive black holes that are, you know, eating a bunch of gas from their galaxy, and they're pretty chaotic. They splutter and they splurt over time. Super interesting to study that variability, but if you're looking at something that's half a universe away, then this thing called relativistic time dilation slows down their sputtering and spurting dramatically. And so you have to remember that and put that fact into your calculation, otherwise you get it all wrong.
Oh, okay. So you do factor it in.
You actually make the adjustment.
Make the adjustment.
Right.
Yeah, fortunately, it's simple algebra. Einstein made that one easy for us.
Mm-hmm.
Right.
Yeah, I have my one paper that is co-authored with a Nobel laureate. I'm the last author on that paper. It's, I think it was the first measurement of time dilation in a supernova light curve. Because you have supernova in the outer universe, we have predictions of how quickly they'll brighten and how slowly they will dim. And so we know what they look like nearby. And out in the universe, it was taking longer for that to happen. So we can say, is this a different kind of supernova? Or you plug in the expansion rate of the universe for its distance, and bada bing, it comes out right as you expect it. So yeah, it wasn't actually happening slower. It was a time dilation effect. So this was profound. Yeah.
That is very cool. By the way, you don't have to qualify being the last author on a Nobel laureate paper. You could just be an author on the paper. Okay.
Okay, it's enough.
All right, here we go. Mm-hmm. This is Cameron.
Oh, by the way, so that the lead author was Brian Schmidt, who won the Nobel Prize for the discovery of dark energy, which was empowered by measurements such as these with supernovae. So, and he's in Australia now, I think, isn't that right?
Yeah, he's been in Aussie for a long time. He was born in the US, I believe, but he's been
he's down under
for the longest time.
Mm-hmm. All right, Chuck, give me more.
moving on to Brendan Gabassi. And Brendan says, hey, this is Brendan from Lansing, Michigan. And is it possible for a black hole of any size to be a quasar, given it has enough matter around it to heat up? And how close would a quasar have to be to the Milky Way in order for us to just see it in the evening sky? And if it's not too much to ask, can you elaborate on the news that is quickly spreading about the hole that's 20 times the size of Earth in the sun? I mean, I don't think that's related to a black hole because our sun could never be
but he's
one.
Still he's got anxiety. But be nice to the people's anxiety, Chuck.
Tell me about, hey man, should I worry about the hole in the sun? There's a black hole, son. Please.
It's a question about holes. That's all it is, right?
That is question about holes. Nice job,
right, man.
Why
don't you take the sun one first? Do you know?
No, the sun one. No, I'm tempted to shift screen and Google that right now, but that would be cheating. Is it a sunspot? Maybe.
Yeah, I mean, sunspots are ordinary sunspots are about the size of the Earth.
Yeah,
but the sun can have storms and explosions that are way bigger than
and
Earth.
We are approaching a solar maximum in terms of magnetic storms.
Right, that's in 2025, I think.
Right.
So
it's on the upswing.
I
saw the Northern Lights from right here on this deck a few weeks ago. For the first time in my life.
Look at that.
And this is New York State.
Well, you saw aurora?
I saw an aurora. It was faint and it was, but it filled the horizon. And, you could see the curtains shifting very slowly.
Nice. Did you see colors? Or just the colors? It has to be,
once our eyes had really adapted, we could see a little bit.
And what's your location now on Earth?
New York State, upstate New York.
Upstate New York.
Upstate New York. Yes, you're far away from city lights.
Yeah, exactly.
Yeah.
So
that wasn't just the Empire State Building changing its colors.
Damn.
Because the Yankees won or something. Okay. Right. Just checking.
So anyway, and it's 20 times they say the size of the Earth, but then when you think about it, how many Earths can you fit inside the sun?
1 million.
110 in diameter. What, 1 million in volume? But yeah.
Yeah. 100 across times cubed is 1 million. Yeah. Right.
So you could put 1 million suns inside the entire ball.
No, 1 million Earths.
1 million Earths. I'm sorry, 1 million Earths inside the ball that is the sun. But you would see what you say, 100 Earths going straight across.
Yeah, about that. But I'm saying, if the sun can hold 1 million Earths, what are you worried about for a whole 20 times?
Exactly, for 20 times the size. Big deal.
That's 20% of the diameter. That's not a small hole. But let's, seems to be shining still. For now.
No, if it's a hole, it wouldn't be 20% of the diameter. It'd be the square root of that.
Right. Now, I'm not getting in a math fight with either one of you. I'm just waiting here for somebody to say who's right. Because I'm not getting involved in this math fight at all. Okay.
Math fight. That's what that is. That's a math. I would say, Chuck, will you back me up here, Chuck? Come on. If you're going to look at a hole that's 20 times the size of Earth, it's not 20% across.
You're right. If that statement was about the projected
size of the hole,
the area of the hole.
Right. Okay. Context matters.
All right, there we go.
I think we have another part of this question that I actually have some expertise in.
Yeah, let's do it. So the rest of it.
Can you have quasars that are small? Like, you can have relatively small black holes. Can they become quasars in the right circumstances? Well, sort of. So any decent sized black hole can form what we call an accretion disk around it. So if you get gas close enough, the gas will form this whirlpool of material that's swirling into the black hole. The whirlpool will heat up, and it's from that heat glow that you get the super bright quasar. Now, a quasar and the related, what we call active galactic nuclei, are when you have a black hole in the center of a galaxy, and they're big. But there are smaller black holes, what we call stellar mass black holes, that are left over after a massive star dies, and these might be 10 times the mass of the sun, up to several tens times the mass of the sun. And these things can form what look like mini quasars, but it's in a very special circumstance, and that's when that black hole happens to fall into a binary orbit or to have formed in the binary orbit with another star. Okay, now if those stars get too close, then the envelope of the living star can spill over into the influence of the black hole, and
so is the black hole eating that star? Is it slowly siphoning off and eating that star?
It's flaying the star.
Exactly.
Flay.
Cannibalizing, vampirizing something. It's eating
I love
that.
Vampirizing. I love that. That's definitely what it's doing.
Sucking its life out. And then, so you get an accretion disk that's relatively small compared to, a quasar, but it's still, solar system size. It's still big. And these are called X-ray binaries because we first saw them from the bright X-ray light that they emit. And these we see through the universe, even in the Milky Way. The nearest one is the Cygnus X1 black hole, which is about 1,000 light years away.
Mm-hmm.
Okay, so we do get mini quasars. So
these are basically nearby baby quasars, in a sense.
Well, baby, except they're not going to grow up to be adult quasars.
Oh, yeah. Wait, so Matt, where's the threshold? What would you say is the threshold between just an active galactic nucleus and what we officially would label as a quasar?
Yeah, the definitions are muddy because these things are very far away. And they all these active galactic nuclei look a bit different depending on, how much gas is going in, how big the black hole is, even what is the orientation of the accretion disk. At some angles, we don't even see it because there's a bunch of gunk surrounding it that blocks it.
So there could be galaxies that are quasars for some parts of the universe and not for others.
Yeah, absolutely.
Yeah, okay. That's interesting. So it's an orientation thing.
Yeah, exactly. But the threshold for a quasar, it's essentially a very luminous active galactic nucleus in which we can see the accretion disk.
Mm-hmm. Right.
So you have these two parameters, the luminosity, which is partially driven by the black hole mass. Okay, bigger black hole mass can support a bigger disk.
Right.
It's complicated.
Now, Matt, what I heard is it's still true, because it's been a while since I've looked at this, that the reason why quasars are all far away is because nearby galaxies that may have once been quasars ate all of their gas.
Right.
They completely consumed their accretion disk. So there's nothing left to radiate.
Belly.
They've eaten it. Is this a fair... because the quasars at the edge of the universe, that's long ago.
Yeah.
And far away. In a galaxy far, far away. The nearby galaxies have lived their early lives. Eaten their... And so we don't have a prevalence of quasars nearby. Is that understanding still accurate?
So the short answer is you're totally right. The longer answer is you're partially right. And there's another effect. So it's true that the universe went through something that we call the quasar epoch, which was ended a few billion years ago, and the quasars. So there was this kind of middle period of the universe's life where the quasars flared up in the biggest galaxies that exist in the universe, and that basically corresponded to when those galaxies were being built. Okay, so as the Big Bang happened, galaxies started being built.
So there was a supply of food for
the biggest galaxies, which had the biggest black holes. Nowadays, those galaxies are basically done being built, and more of the galaxy building action is for the lower mass galaxies, like some spiral galaxies, a bit more like the Milky Way. And these things don't tend to create big quasars. But the other effect is that quasars, like full-blown quasars, aren't that common in the universe, and so we don't even have a galaxy that would have been one very close to us.
Right. Mm-hmm. So now you say they're not that prevalent or common in the universe. Could there still be a lot more that we haven't seen? Just because how much of the night sky have we actually seen? You know what I mean? Can you, or does it work out that what we have seen, you can extrapolate and say that we're going to see that exact amount if we were to see everything?
Yeah, I mean, I think you answered the question, Chuck, so thanks. But we've seen a lot of the universe. Our surveys have scanned a huge volume of the universe. It's hard to look directly through the disk of the Milky Way because there's too much stuff in the way, but above and below we've seen a lot, and we've found many hundreds of thousands of quasars there. Okay, so I say they're not common, but the universe is big.
But we see them. Okay.
Yeah, it's big. A big universe.
Yeah,
rare
right.
things are common.
Or abundant or something, yeah.
It makes perfect sense.
Makes perfect sense, right?
It just makes perfect sense. You can't get any simpler than that. All right. This is Cameron Bellamy who says, greetings from Baltimore,
But just to be
Maryland.
clear, if 1 in a million people is 7 feet tall, then in a country of 300 million people, they're 307 foot taller. So,
But you still might not get on the basketball team.
yeah,
Right.
the big numbers bail you out of that. When it comes down. And of course, what's the adjective we have for big numbers? They would be astronomical. Yes.
Oh,
We kind of corner the big numbers, don't we?
Yeah, we totally own the big numbers.
yeah, that's you guys.
We got all
That's
the big
for-
numbers.
All right, give me another one.
This is Cameron Bellamy. He says, greetings from Baltimore, Maryland. On this show, Neil has talked about the consequences of our expanding universe and its eventual big rip. I'm curious how this phenomenon will affect black holes. From my understanding, black holes are super dense matter, and space-time expands. Will the super dense black holes become less dense until eventually representing matter density similar to what the rest of the universe has, and thereby being able to be ripped? Will the opportunity for life arise from what was once a black hole as the universe expands in the far distant future?
Damn, my boy's thinking about this.
And
stuff.
let me tell you,
question.
this question he should have followed up with, and it only took me 1 year to think of this question.
We're going to pick up the answer to that at the beginning of segment 3, right after this break. We're back, Cosmic Queries, based on the expertise of my friend and colleague, Matt O'Dowd, who teaches at Lehman College of the City University of New York. And Matt, how do we find you on social media? Beyond your YouTube channel, which has 3 million followers.
Yeah, so you could go to PBS Space Time and just watch me talk about space and quantum mechanics and everything
All
physics.
good. I've seen episodes. You're great. You're totally
thanks, man.
there, friendly,
Thanks, man.
and
That means a lot.
informative, and I always want more when I see it. So congratulations on what you've created there. And
Appreciate
it's a part of the PBS universe, I guess, right?
Yeah, it's a PBS show.
Okay.
PBS Digital Studios, to be precise.
Nice.
Otherwise, I am Matt of Earth _ on Twitter and on Instagram.
Matt of
Matt of Earth.
Of Earth.
Earth.
Yeah,
Earth.
This
Matt of
is
Earth.
Earth's Matt.
This is Earth, Matt. Yeah.
Okay.
Mars has its
is-
own Matt. Apparently, I didn't know that.
Just in case people are wondering. Yeah.
Chucky's getting ready for the aliens.
There you go. Exactly. If they come here
Oh, that Matt,
if they
not
come
the other
here
Matt.
and they say, take us to your mat, we will know. We will know.
We want to go to the Matt on this one.
Where's Matt? Then we'll know. Yeah, of course, everybody knows Matt of Earth. That's why we're here.
All right, we're picking up where we left off.
We had Cameron Bellamy, who basically was saying, when you look at the Big Rip and you consider black
Will it
holes,
affect black holes? Yeah.
will it
what
affect
happens?
black holes, and does it affect them differently because they're so dense?
Yeah. What do you know about that, Matt?
Yeah, so this is pretty speculative, but I'm going to take my best guess. So the Big Rip is probably not going to happen. It only happens if dark energy is something more exotic than most physicists think it is. If the strength of dark energy increases over time, then eventually the accelerating expansion of the universe can affect smaller and smaller regions, eventually subatomic scales tearing everything apart, blah, blah.
Right.
Okay, so if that's the case, then it would affect black holes, I think, because black holes contain space, and if that space contains an increasing amount of dark energy, that dark energy has an anti-gravitational effect. I think what it would do would be to cause black holes to evaporate more quickly.
Quickly.
That would be my guess. So black holes are evaporating, as we learn, by Hawking radiation. My guess, so the event horizon's shrinking. So my guess is that a Big Rip style dark energy would cause that evaporation to happen.
So
more
my
quickly.
guess, I like to hear what you said there. My guess is that the opposite will happen, is
Okay.
that they'll evaporate less quickly because the expansion dilutes the energy density in their environment
around the black hole,
around them, and which will make it less likely to produce the particles. However, what you said seems to be all in, where the black hole volume is made of space-time like anything outside the volume, and it's space-time that's getting stretched.
Yeah.
So I can imagine the Big Rip simply unzipping black holes.
Right.
And because it's stretching them out so that they no longer have their black hole event horizon density.
Yeah, I bet someone has calculated this.
Yeah, so I haven't calculated, but some combination of our two answers sound like is going to be it.
Exactly.
Now, let's get back real quick, because I know we don't have a lot of time left in the show, because we got to get to more questions.
Do it.
Please go back to why the Big Rip is not going to happen, because you're the first person.
No. It will happen if the strength of this dark energy grows relative to gravity as the universe expands.
Okay.
It will happen. What Matt was saying is we're not entirely sure that dark energy will grow in strength as the universe expands relative. Did I characterize you correctly there?
Yeah, the default model for dark energy is that it maintains a constant energy density.
Okay, I got you. Yeah. Now I'm totally straight now. Okay, great.
Okay.
That's awesome. All right, let's go to our friend, Alejandro Reynoso.
I have to assume he's not offended by this, Chuck, because otherwise we would have gotten mail from him by now.
We have not. As a matter, we have not received any cease and desist orders from Alejandro Reynoso. So Alejandro Reynoso says, "This is Alejandro Reynoso from Monterrey, Mexico," and he says, "Hello."
Okay.
Or should I say, hola? How do you use gravitational lensing in your observations? Does it actually let you see distant objects clearly, or do you need to make many adjustments to come up with your image? So how are you utilizing gravitational lensing?
Yeah, Matt, what does your object look like after it's been gravitationally lensed?
Great. I love this question because I know about it. For one, so the Einstein guy again predicted that gravitational fields bend the path of light, bend the fabric of space-time. And so you look out there in the universe and you see that distant objects aren't necessarily where they appear to be, particularly if there's something big like a whole galaxy between you and that object. The things that I'm interested in are gravitationally lensed quasars. There we go, quasars again, where you have a distant quasar, an intervening galaxy, and you just happen to be perfectly lined up so that the light from that distant quasar is deflected by the gravitational field and comes back towards us. And so we actually see the same quasar through multiple paths through space. We get light from multiple different paths through space. So what it looks like is multiple images, sometimes just 2 images of the same quasar, sometimes 4. So you actually looks like you see 2 images or 4 images, but really there's always an odd number of images. And that's because in between the 2 images or the 4 images, there's a tiny little image of the original object. Normally you can't see that because you've got this great big galaxy or whatever is doing the lensing in the way. But yeah, fun fact, you always get an odd number of images with gravitational lensing. So my interest is in trying to use gravitational lensing to probe the inner structure of those quasars. So you have this giant accretion disk around the black hole, but really these things are so far away that there's no telescope that we can even imagine building that'll be able to take a real picture of a quasar and see that inner structure. But in the case of gravitational lensing, you can basically reconstruct what the quasar looks like because you have one more effect at play. So the lens, if it's a galaxy, is a pretty crappy lens. It's made of stars. And because everything in the universe is moving relative to each other, you see occasionally you'll get this extra special alignment of a star inside the lensing galaxy with one of these one of these pathways. So one of these pathways might pass in the gravitational field of an individual star with such an alignment that that one image grows in brightness and then shrinks again. And so over time, you see these, let's say there are 4 images, you see them flicker on different timescales. And from that flickering, you can actually reconstruct the inner structure of the quasar, because the rate of the flickering depends on how big the quasar is. And so you can sort of map it out in this way.
Mm. And I remember I was active in graduate school when this first measurement was made, where someone looked at one of the lensed quasars and it flared in some way, and then they waited for the other image to flare.
Yeah.
And it flared in exactly the same way. And that time delay was the path length difference between one direction around the object and the other. I mean, it was a brilliant thing. Everyone was sitting around waiting for it, and bada bing, there it is.
Yep.
That is really cool.
Yep. And you know
that's how you knew it was the same object.
It had to be the same. It was just on a delay. Because it did the exact
exactly the same thing.
Wow.
I know. I felt the same way.
That is so cool.
Because initially you don't know what it's this object in the image.
Right.
And so I was in graduate school when that happened. That's how old I am, Matt. I'm like decades older than you. So I'm remembering when this stuff
Not
was...
too many, I don't think. Well, that exact thing, like measuring the different path lengths, is going to be one of the ways that we actually figure out what dark energy is. Because if you can measure those different path lengths, you can get the distances to the lens, to the quasar, and so you can actually map the expansion history of the universe by getting those distances. And that's one of the ways we might be able to figure out the rate at which the universe is accelerating.
Mm-hmm.
Because, oh my God, that's it. Because the universe is actually not just expanding at a constant rate, it's speeding up. So when you're able to get those distances and see the differences on the delay, you can actually kind of calculate the dark energy, because that's what's behind it, right?
Exactly.
Yeah.
Damn!
Yep.
Gosh, doggone! Science is amazing! Wow. Okay, that's amazing.
No, but there's still
ahead.
people who walk among us and say, I don't have science. I don't make science.
If that doesn't get you, nothing will. That is some amazing stuff right there. All right, here we go.
All right.
This is Renee
Keep
Skirp.
going.
Renee Skirp says, hey, guys, I just heard about the red star Arcturus, and that I could have a planet or substellar object orbiting it 12 times larger than Jupiter. About a month ago, you had a guest on that said Jupiter was the largest planet ever discovered. So what do you think could be orbiting? Can't wait to hear the answer. Thanks from Orange County, California, Renee.
Okay, I don't know that we had a guest that said Jupiter was the largest planet ever, because it's definitely not. All right, plenty of other planets in the exoplanet catalog are bigger than Jupiter. The difference is, if you start getting much bigger than Jupiter, we don't really call them planets anymore, right? I mean, they're like brown dwarfs. We have other vocabulary for them. So that's really what's going on here.
They're failed stars.
Failed star. Matt, do you have any insight into that question?
Yeah, I mean, I'm not aware of this result, but 10 times larger, 12 times larger than Jupiter is really getting on the verge of the smallest star level. Well, 100. So it's a brown dwarf. So the question is it a planet or is it a failed star? And I think the answer is it depends on how it formed. You know, if the two form together by, collapsing from the same giant cloud of gas and finding each other, then it's a binary star system. One of them is just a failed star. But if the big star formed first and then this giant Jupiter formed in the disk of leftovers around that star, then you might call it a giant planet.
Yeah, so the origin story matters.
Yeah,
the origin story matters, it sounds like.
That makes sense. So one's cleaning up stuff.
Yeah, exactly.
And the other
one is out of the same birth
out
sac.
of the same, right. Wow.
Right.
Okay, cool, man. Yo, that was a cool question, Renee. Thanks. I
All right.
dig it.
Okay.
Here we go. Trisha Lynch says, hello and greetings from Beaverton, Oregon. My question is, what would happen if galaxies stopped rotating? What would happen?
It wouldn't be good. Let me tell you that.
Next question.
There you go. Thank you, folks, and good night. There you go, Trisha. Hope you can sleep.
No. I got one. I'm going to tee up Matt on this one. You ready? So if the Milky Way stopped rotating today, then every single star would fall to the center.
Yeah.
Because it's its orbital speed that's maintaining our distance. Without that orbital speed, they will fall to the center. And Matt, what do you have waiting for everybody at the center? Behind door number 1, Matt.
My favorite cosmic friend, the supermassive black hole.
There you go.
Sagittarius A star, 4 million suns worth of black hole. And if they really stopped perfectly, then technically everything would, well, yeah, it would be a mess. It would be a mess.
It would go straight to that black hole.
Well,
it wouldn't be 4 million. It would be billions of times the mass of the sun.
Is the black hole exactly in the center of the Milky Way?
I'm
not sure.
Oh.
So they might do close. Everything would end up in these.
I didn't know if it's exactly in the center. Good question.
Crossy things, but there'd be collisions and.
Yeah, it would be bad.
Yeah.
All around, and the whole galaxy could just be eaten by the black hole at that point. And that would be interesting.
Wow. All right. Yo, that'd
be something Thanos would do.
Yeah, it would be. Just you
don't
Except
like me when I'm angry.
He doesn't snap a finger. He actually claps like like the clapper that turns the lights off. You're like, and then everything just falls to the supermassive black hole in the center of the galaxy.
Or the choreographer on Broadway. Step up to the thing. Yeah, that's how to destroy a galaxy on the spot and make a super duper massive black hole.
Look at that. Right. Ignacio Carasconi says, or Caracasoni says, hey, greetings from Brooklyn, New York. My kid and I are fans of the show. That's right. And we have been to...
he and who are fans?
My kid and I are fans of the show. And we have been to the Hayden Planetarium at least a dozen times.
Nice.
So my question for Matthew, Neil, and hello, Chuck. He ain't asking me anything. Just saying hi.
Okay.
He says, why is solar gravitational lens mission hasn't happened yet? And when is it likely? One of the most powerful tools to study exoplanets and find life besides our local sample. When will that happen?
Ooh, Matt, do you think he's talking about the lensing that Bogdan Pachynski was doing, the micro lensing? Do you think that's what he's talking about there?
So this is a plan to send out a little telescope to a point in the outer solar system. So there's a point in way out beyond, Neptune. I was going to say Pluto, then I realized you were here.
Yeah, that's right.
Way beyond Neptune. And so there's this point where, and so you got the sun. The sun is a big gravitational object. It bends the path of light. And there's this region, can't remember how far away it is. It's like a week light travel time away or something like that, where light from a distant object will come to a focus due to the sun's gravitational field. And if you could put a telescope in this focal
I remember
range,
this telescope.
Yeah,
yes.
Yeah. This sort of, and it extends over a certain range because it depends on how far away the object is. But if you could put a telescope there, then the sun would become an extra lens on that telescope, and it would produce such powerful magnification that you could see, so the calculations go, a single planet orbiting around a distant star, which is something that is extremely difficult for us to do.
I remember this, but then I stopped reading about it. So has this idea gone away?
No, it hasn't gone away. People have been thinking about it for a long time and are still I hear people talking about it and
but wait, but Matt, isn't the sun in the way? How are you going to see a lensed planet when the sun is brighter than everything? It's like trying to find a firefly in a Hollywood searchlight. How does this actually work? I agree, and I see where you get the magnification effect. That would be amazing. I get that, but there's still the matter of this. I guess you have to have some kind of some kind of disc that blocks the sunlight. in the telescope? You'd have to have something like that.
Yeah, I love it when you ask me a question and then answer it perfectly. So, I mean,
I'm just thinking it up on the fly.
You know, I'm sure you know about coronagraphs, we call them.
Yeah.
So you would, and there are ideas about how you would build these giant coronagraphs, basically a big circle, but there are also various interesting complex things that would unfurl in front of this distant telescope that would block the sun's light. And so you could see this, basically this ring. So what it would look like would be the sun blotted out, but then surrounding the sun, this perfect ring, what we call an Einstein ring. And that perfect ring would be the exoplanet. Okay, so if it were another civilization doing this for the Earth, they would use their star to look at the Earth. If they just happened to be in the right position to do that, and then Earth's structure would be smeared around, but to the level that if you reconstruct it, and you could reconstruct it just by using good old Einstein general relativity to figure out what the image looked like, and
so anybody could do it, right?
Yeah, anybody could do it. Literally anybody. You could see, continental coastlines down to, I can't remember the exact scale, but kilometers or something like that. So you could literally map the surface of that distant.
But you'd have to reconstruct the sphere from the smeared circle.
Exactly.
Right. The visual image from that, right? So that'd be a task that would be.
Okay.
I forgot all about that telescope. Matt, thanks for reminding me of that.
I got to tell you the truth. It sounds like the worst camera ever. I'm sorry. It really does. I don't want to be a hater, but I'm just saying.
Chuck hating on the most advanced system.
No, I'm joking.
All right. Matt, we got to call it quits there. Man, that went fast.
Sounds good.
All right.
I'm sad, but.
Well, you know what? Let me give you one quick one because this guy is personal and professional. This question, it's a personal, professional question. This is David Lays, and he says, "Hello, Dr. O'Dowd. Have there been any surprise findings in your research that have shaken up your understanding of astrophysics?"
In my personal research,
in your personal research,
I wish. In my personal research, have I shaken up the understanding of my? Oh man. Now I'm going to get sad because I don't think I have personally revolutionized my own understanding. There have been things that have surprised me. There's been objects that I've studied that have surprised the hell out of me. Gravitational lenses that have done things that I really didn't expect them to. I have managed to find ways to look at the interiors of quasars that are relatively new and found things like
so it's not a new object, it's a new tactic.
A new tactic.
Yeah. New tactics.
But
you're a little hard on yourself there,
I know,
Matt.
right, man.
You're a little hard on yourself. Yeah.
There's some weird stuff out there.
And for everybody listening, you just found out the heart of every scientist right there in that question and answer. Because scientists, what they don't want to do is succeed. What they want to do is look down and go, what the F is that? What? What the F is that? Oh my God, come over here. What is that? That's what gets scientists all freaked out.
That's how it works. Yeah, it's not the discovery of what you know. It's finding something you have no idea what the hell you're looking at. Right. All right, dudes, we got to call it quits there. So thank you for yet another episode of StarTalk Cosmic Queries. Neil deGrasse Tyson here, as always, bidding you to keep looking up.